So we will now evaluate the remaining terms of matrix R. So for I equal to 1 and j equal to 1, the term that we will evaluate is R1 comma 2. This means first row second column, and this will be given my minimum for k belongs to 2 3 4 5 R of k comma j is 1. Okay, so here it is j plus 1, so j is 1 plus w of k comma I. So that will be for I equal to 1, that will be, this is 1, k comma 1. So this will be minimum of R of 1 comma 1 plus w 1 comma 1, or R of 2 comma 1 plus w 2 comma 1. So R of 3 comma 1 plus w 3 comma 1, R of 4 comma 1 plus w 4 comma 1, and R of 5 comma 1 plus w 5 comma 1. Okay, so the value in the first column of matrix R is 0. This is 0. Okay, so directly you can refer the adjacency matrix, and 1 comma 1 means this value, first row first column, 2 comma 1 second row first column, 3 comma 1. So these belongs to first column in adjacency matrix. Okay, so you have to select the minimum one, so you can easily select the minimum is 0. Okay, now for I equal to 2, the expression will become R of 2 comma 2 minimum k belongs to 1 2 4 5, R of k comma 1, j is 1 plus wk comma 2. Okay, so again here for different values of k comma 1 comma 1 2 comma 1, this refers to first column in matrix R, which is 0. So directly you can refer the second column in weight adjacency matrix, and you can select the minimum one, 0. So value will be 0. Okay, no need to do this tedious computations again and again. For third, you can refer minimum in third column. So this is minus 2. Fourth column is, this is minus 1, and this, and last minimum is 0. One more thing is that the value of the fifth column in matrix R will be always 0, so you can directly write 0 at this point. So this will save your calculation time. So I will calculate for one more column, and then you can evaluate for the last one. Yes, for this j will be 2, and equation will be R of I comma 2 3 at this point, R of I comma 3 minimum of R of k comma 2 plus w k comma I, and the value of k is 1 2 3 4 and 5. So for I equal to 1, R of 1 comma 3 will be given by minimum value of R of 1 comma 2 plus w 1 comma 1, or R of 2 comma 2 plus w 2 comma 1, R of 3 comma 2 plus w 3 comma 1, R of 4 comma 2 plus w 4 comma 1, or R of 5 comma 2 w 5 comma 1. Okay, so this is equal to r of 1 comma 2 is 0 and 1 comma 1 is 0. 0 plus 0 equal to 0. Second term is r of 2 comma 2 plus r of 2 comma 1. So again 0 plus 0 is 0. Next term is r of 3 comma 2. 3 comma 2 is minus 2 and w3 comma 1. 3 comma 1 is 4. Next is r of 3 comma 2, that is minus 2 plus w3 comma 1. So 3 comma 1 is infinite. Next is r of 4 comma 2, that is minus 1 plus 4 comma 1 of w matrix. So 1 plus infinite, that is again infinite. And 5 comma 2, 5 comma 2 is 0 and 5 comma 1 is 0. So 0 0 gives 0. So minimum is 0. Okay, so if you carefully observe at this point, what when we are calculating the values corresponding to the third column, what we are doing, we are referring the values of second column, and for I equal to 1 we are referring the values of first column in matrix W. Okay, so first value of matrix R, first value of matrix W, add them. Then second value of matrix R, second value of matrix W, add them. Then third value of matrix R, third value of matrix W, add them. That's what we are doing. Okay, and choose the minimum, that is 0. Same thing you have to do for 2 comma 3. So you have to refer the second column of matrix R and you have to refer for I equal to 2 second column of matrix W. So just you can without writing this in a tedious way, you can just calculate it quickly. So infinity plus 0 gives infinity, 0 plus 0 gives 0, 4 minus 2 gives 2, 2 minus 1 gives 1, and 0 plus 0 gives 0. So value is 0. For 3 comma 3 you have to refer the third column of matrix W, and this will be the same second column of matrix R. So 0 minus 1 gives minus 1, 0 plus 0 gives 0. Okay, so first is minus 1, then 0. Infinite, whenever it is infinite, the answer will be always infinite. 0 minus 2 gives minus 2, and 0 minus 1 gives minus 1. So minimum is minus 2. Okay, directly you can write without expanding this term exhaustively. When you will calculate for column 4, the answer will be same, 0 0 minus 2 minus 1. So the value of r1 is 0, r2 is 0, r1 is this 1 comma 4, r2 is 2 comma 4, r3 is minus 2, and r4 is minus 1. Okay, now you have to draw the retimed graph. So for this you have to calculate the weight of the edges in the retimed graph. So weight of edges in the retimed graph u to v is given by w u to v plus rv minus ru, and edges present in the graph are 1 to 2, 2 to 3, 2 to 4, 3 to 1, and 4 to 1. And we is 0 5 3 0 0, and r1 is equal to 1 0, r2 is equal to 0, R3 is -2 and R4 is -1. So I have sufficient information to calculate the weight of the edges in the retime graph. Okay, so WR122 will be given by W122 plus R2 minus R1, and that will be W122 is 0 plus R2 is 0 minus 0, that is 0. WR223 is given by W223 plus R3 minus R2, and that is equal to 5 minus 2 minus 0, that is 3, and WR224 will be given by W224 plus R4 minus R2, and this is 3 minus 1 minus 0, that is 2. Okay. WR3 to 1 is 3 to 1, W3 to 1 plus R1 minus R3, so 0 plus 0 minus of minus 2, that is plus 2, and at last WR4 to 1 is W4 to 1 plus R1 minus R4, this is 0 plus 0 minus of minus 1, that is plus 1. Okay, so now we can draw the retime graph for the given DFG. So using the new weight, I have drawn the retime graph. Okay, so WR1 to 2 is having weight 0, WR2 to 4 is having weight 2, WR2 to 3 is having weight 3, so 2 is already present, just I have to add one delay, so total 3 delays. 3 to 1 weight 2 and 4 to 1 weight 1. Okay, this is the retime graph, and now I can write folding equation for this. So you can write folding equations using the formula dfu to v n into w e minus p plus v minus u. So for all the edges you can calculate the folding values using this formula. So starting from equation 1, this is df 1 to 2, folding order is 2, weight is 0 minus 1 plus 1 minus 0, so this is 0. For df 2 to 4, 2 into 2 delay elements minus p is 1 because it is an adder, plus 0 minus 1, so this is 2. df 2 to 3 will be given by 2 into total 3 delay elements, 2 is an adder, plus v is 1 and u is also 1, so it is 5. df 3 to 1 is 3 to 1 is 2 delay element is in between 2. Node 3 is a multiplier, so P will be 2 and 0 minus 1. So this is 1. And finally DF 4 to 1. 1 delay element is in between 2 into 1. 4 is an multiplier, so PU is 2 minus 2 plus V minus U is 0 minus 0. So this is 0. Okay, no negative value. So to draw the folded circuit, we have following informations. First is that we have one staged pipeline adder, two staged pipeline multiplier. Folding set for A is node 1 and 2. Folding set for M, that is multiplier, is 3 and 4. A is adder, M is multiplier. Folding order is 2, and also the iteration period N is also 2. It can be calculated from the circuit very easily. Okay, so this is the critical path 1 plus 1 2. So, or individually for this multiplier, the computation time is also 2. So T sampling is 2. So iteration, in other words, I can say that T iteration is also 2. And also it is given that iteration period is 2. So this, the input of this adders are connected to a switch. This switch will be connected to this point at instance 12 plus 0 and to the second point at 12 plus 1. Okay, same here, same for this case. Since the iteration period is having two cycles, so first cycle is 12 plus 0 and second cycle is 12 plus 1. So during 0th cycle, the adder will complete the task of adder number 1. Okay, so it will complete the task of adder number 1. So it is receiving input from node 3 and node 4. So one input from multiplier will be connected to 12 plus 0 of this input, and second input of the multiplier will be connected to 12 plus 0 of the second input. Okay, how many delay should be in between? That will be given by this equation, 3 to 1 and 4 to 1. So df 3 to 1 is 1 and df 4 to 1 is 0. So one of the input should be connected to this multiplier with one delay in between, and second input should be connected with 0 delays. So it is connected accordingly, one delay element in between and no delay element. Okay, with the use of this two folding equations. Okay, now second input. So during the second cycle 12 plus 1, this adder will complete the task of adder number 2, and adder number 2 is receiving one of the input from node 1. Okay, either you can refer this circuit or you can refer this folding equation. So adder number 2 is receiving input from node 1 and second input is from external source, and one is adder, node 1 is adder, means output of adder should be connected to its own input with 0 delay, and second is external source. Okay, so at this point I can provide external source XN, and this I can connect directly, the output of adder connected to its own input with 0 delay. So this completes the connection of adder. Similarly, the inputs of multiplier can be connected. Okay, so this multiplier will complete the task of multiplier number 3 first and then 4. So multiplier 3, one of its input is B and A. Okay, So A and B are constant. So I can directly give A at 12 plus 0 and B at 12 plus 1. And for second input of this multiplier, considering multiplier 4, it is receiving its input from node number 2. So 2 to 4, the value is 2. Okay. And 2 is an adder. So output of the adder should be connected to the 12 plus 0 input with 2 delay element in between. Similarly, I can evaluate for multiplier number 3. So it is also receiving its input from node 2, which is an adder. So 2 to 3 gives 5. Okay, so output of the adder with 5 delay elements in between, and that should be connected to this point. So I have already included 2 delays. I have to just add 3 more delay, and output of that can be connected to this point. So the output is taken from node number 2, and it is processing the result at first cycle. So the result will be available in next cycle, that is 0th cycle. Okay, because it is having just 2 cycles in iteration. So the output will be taken from the adder, and the switch will close at the instance 12 plus 0. So this is the final folded architecture for this IAR filter, and this was derived by retiming the given IAR filter. Total number of registers used in this architecture is 5. Total delays is 5. So next we will minimize the number of registers in the folded architecture. So for register minimization, we have to first calculate the lifetimes of the variables. Then we will prepare a lifetime chart, and then we will calculate the maximum number of minimum number of registers required to implement the given architecture, and then we will allocate the variables to the registers in respective cycles, and based on this information we will finally draw the folded architecture. So starting with calculation of lifetime can be calculated by the formula T input is equal to U plus PU, and T output is given by U plus PU plus maximum df u to v. Okay, so one by one we will calculate lifetimes. So for node 1 is adder, U is 0 and PU is 1, so 1, and T output is U plus PU plus max df u to v. So U plus PU is already, we have calculated 1, max v df u to v. So max v df u to v means U in this case is 1, so we have to consider all the edges starting from U and ending at V. Okay, and we have to take the maximum value. So edge starting from 1, there is only one value and it is 0. Okay, so T input T output both are equal. For node number 2, U will be 1, PU will be also equal to 1, so 1 plus 1 is 2, and T output will be, just we have to add this factor. So node edge starting from node number 2, so we have two different edges, 2 to 3 and 2 to 4, and this is the maximum one, so we have to consider this maximum value. Okay, so 2 plus 5 gives 7. for node number 3. Okay, node 3 is a multiplier and it will be executed. Small u will be 1 for this. So 1 plus pu will be 2 in this case. So the input will be 3 and dfu to be 3 to 1, only one value is there. So 3 plus 1 is 4 and 4 u value of 4 is 0. 0 plus 2 gives 2 and 4 to 1 is 0. Only one option we have and the value is 0. Okay, so the output is also 0. So in this case we are also calculating the lifetimes of node number 2. In a FIR filter we had not calculated the lifetime of the node which is producing output, but in this case the output value is also used by other computational element like node number 4, node number 3. Okay, so yn minus 3, yn minus 5. So based on this lifetime table, now we can prepare a lifetime chart. So we have to consider total 7 number of cycles, the maximum value of the output, and we have total 4 nodes, and starting from node 1 it is generated at first cycle and consumed in the same. So we'll put across. For node number 2 generated at second cycle and consumed at 7th. So 2 to 7. For node number 3, 3 to 4, and for node number 4, 2 to 2. So we'll put across. Now we will calculate the live variable. Okay, and the iteration period for this given filter is 2. So this is 0th iteration, this is first iteration, this is second iteration, and this is third iteration. So for 0th iteration we can calculate directly 0 live variable, 0 live variable. For first iteration, node 2 has just generated its output, but it will not be considered as live, and 4 it doesn't require register. So live variable is 0 at this point. And refer the previous iteration, 0th cycle, the value is 0. So 0 plus 0 is 0. In third cycle, this is live and this is just generated. So live variable is 1. And refer previous cycle, first cycle, value is 0. Add 0 to this. In next, 2 live variable, previous iteration, second cycle, the value is 0. 2 plus 0 is 2. At this point only one live variable, and refer third cycle of first iteration, that is 1 plus 1 is 2. At this point one live variable, therefore fourth cycle of second iteration, 2 live variable, 1 plus 2 is 3. At this point one live variable, and in fifth cycle 2 1 plus 2 is 3.